Section 20.12 will look at protecting groups, and let's look at a reason for why they might be needed. So here we have a reaction where we want to add our methyl magnesium bromide to our ketone to reduce the ketone and add an alkyl group. However, the problem that we get is that we have an alcohol here. So instead of our methyl group coming here and attacking the carbonyl like we'd like it to do the addition reaction, instead it will come over here and deprotonate the alcohol. And why does that happen? Because on this side we have an alcohol, which is a stronger acid. Again, it's back to pKa's. On this side we would have methane, which is a weaker acid. So anytime that there's an alcohol around, or water around, like we talked about before, we can't use organometallic compounds to do an addition to a carbonyl. So what we're going to have to do is we're going to have to use what's called a protecting group. We want to hide the alcohol and make it not look like an alcohol for a while, but then we want to be able to get it back later. So there's always a three-step process for using protecting groups. The first step is to protect, which is to convert your group, in this case an alcohol, into another functional group that does not interfere with the desired reaction. Then once you protect, you're going to do any reactions that you want to do. So react, this would be to carry out the desired reaction. And last, we want to deprotect. And in deprotection, we want to recover the original functional group. In this case, the alcohol. So again, we'll start with a molecule that has a ketone and an alcohol in it at the same time. And now, before we can react our ketone with our organometallic compound to reduce it and to add an alkyl group to the molecule, we need to hide or protect this alcohol. So we'll react this with T-butyl dimethyl silyl-chloride, or TBDMS chloride, it's sometimes abbreviated, in the presence of imidazole. So the question that we always want to get back to is the question of who has electrons and who wants them. Our oxygen has 2 lone pairs of electrons. And hopefully you remember from a lot of things that we've done before, anytime that you have a carbon halogen bond, it's very polarized, and the halogen is a good leaving group. So a silicon halogen bond is actually quite similar. So one of the lone pairs on the alcohol can come up and attack the silicon, and the chloride can leave with its pair of electrons, since it makes a good leaving group. And remember, the reason it's a good leaving group is because it's the conjugate base of a very strong acid. So that makes this intermediate that has a protonated version of the alcohol, which no longer now is an alcohol, now it's a silyl ether. And we have lone pairs of electrons on our amine, which is a base, and a lone pair from this nitrogen can come over and take this proton, pushing the electron pair back onto oxygen to get rid of the positive charge. And now we don't have an alcohol anymore, now we have a silyl ether. So we have our ketone up here, which we can now react. Our alcohol is hidden or protected as a silyl ether. So you can write this out with the full structure like this. You can also abbreviate it as OTBDMS, T-butyl dimethyl silyl. And what that says is that that's the T-butyl dimethyl silyl ether from our original alcohol. Now, once this alcohol is protected, I can react this with my Grignard reagent. So in this case, I'm reacting with propyl magnesium chloride. Now my propyl group can attack my carbonyl. And as it enters there, it pushes this electron pair out onto oxygen to make the intermediate. So now I've added my propyl group and I have my alkoxide. I can reprotonate that with water to get my final product, or my alcohol. So now, by protecting my alcohol that I had down here as a silyl ether, I'm able to react my ketone with a Grignard reagent or any organometallic to add the alkyl group and reduce my ketone to an alcohol. Now, once I get there, what I want to do is I want to deprotect this. So to remove this silyl ether and get our alcohol back, we need something that's going to react with the silicon. Silicon and fluorine make a very strong bond together, so usually we want something that's going to deliver fluoride ion. Now, sodium fluoride would work just fine, but a lot of times we're working in organic solvents because we have big organic molecules. So what we do is we can make tetrabutyl ammonium fluoride, and with these big butyl groups on here, that makes this much more soluble in an organic solvent than sodium fluoride would be. So TBAF, or tetrabutyl ammonium fluoride, is a common way of deprotecting silyl groups. So let's take a look at the deprotection mechanism. I'll just blow up the t-butyl silyl ether part. So the fluoride comes in to create a new bond to the silicon. When it does that, it'll break this bond between silicon and oxygen. This electron pair goes back onto oxygen to make an alkoxide again. Which finally then just gets reprotonated with water to make the final product. And now we have our alcohol back that we started with, that we first protected with the TBDMS group, and we've added our Grignard reagent. So we did our protection, we did our reaction, and then we did our deprotection. So protect, react, deprotect. That'll always be the sequence when you work with protecting groups.